Measuring time can be very useful when we want our robot to be able to act based on external events, detected through the sensors attached to the robot. To measure time, we use a timer. First, we are going to see how we measure time, without using ODI. In particular, assume that we want to measure the duration of a task. Here is how we do it. When the task starts, we click on this command block or press the up arrow. As a result, the timer is set to 0 and starts counting time. When the task is over, we click on this command block or press the down arrow. As a result, the current value of the timer is stored in the variable named measured time. Note that we have already seen what variables are and how they are created and used. So let's do it. You can see that the second click occurred 4.6 seconds after the first click. Let's do it again. This time, the time difference between the two clicks is 5.1 seconds. Let us now go to ODI and see how timers can help us achieve advanced stuff. Assume that we want ODI to go forward for 2 seconds. How do we allow something to happen for a given time interval? There exists a simple way to do this. Just execute this program. The motors are initially set for moving forward and then the program freezes for 2 seconds, allowing ODI to move forward for 2 seconds. When the 2 seconds have passed, the execution of the program continues and the last 2 commands are executed, forcing ODI to stop. This is the simple way to allow something to happen for a given time period, but this simplicity comes with a price. An intuitive way to explain this price is to say that during these 2 seconds, ODI is put to sleep, meaning that no other command is allowed to be executed. As a result, during the given time interval, ODI cannot respond to external events. To explain this using an analogy to real life, assume that we are driving a car and we want to allow the car to move forward for a given time interval, say, 2 seconds. Using the wait command is to set the car for moving forward and then somehow make the driver unable to see or hear anything. If something happens within these 2 seconds that requires a response on the driver's behalf, this response cannot be triggered. A better approach is to use a timer. When the car starts moving forward, we set the timer to 0. Then we continue driving the car, paying attention to the road, but also check the timer frequently. We are now able to respond to external events and, for example, hit the brakes if we need to. Checking the timer is a very fast process that does not distract us from the driving task long enough to miss an event. We stop when, according to the timer, 2 seconds have passed. So here it is. Assume that we want ODI to move forward as long as there is no obstacle in front of it, and we want ODI to do this for 2 seconds. Said otherwise, if no obstacle is detected, ODI will move for 2 seconds. If, within these 2 seconds an obstacle appears, ODI will stop and remain stopped until the 2 seconds have passed, or until the obstacle is removed. This small animation visualizes what ODI must do. And this is the program that does it. We have expanded the time period to 5 seconds in order to have enough time to put a few obstacles. Observe that we have a loop that will run until the value of the timer becomes greater than 5. Before the loop, the timer is set to 0 and starts counting time. A logical question would be the following: since we want ODI's behavior to last for 5 seconds, why don't we make the loop stop when the timer is equal to 5, instead of greater than 5? So let us assume that the loop ends when the timer is equal to 5. Remember that the instructions inside the loop take some time to be executed. Let us assume that each execution of the loop needs 0.01 seconds. Assume now that when the timer is checked, its value is 4.995 seconds. Since it is not equal to 5, the loop will be executed again, and as already said, this takes some time so that when the timer is checked again, its value is 5.005. Again, it is not equal to 5, so the loop continues. It follows that this loop will never end, because the value of the counter cannot become 5 in the future. But with the current stopping condition, the loop will not be executed again and the commands below the loop are next. As a result, OD will stop. Note that with the program as shown here, if the timer is checked when its value is equal to 5, the loop will be executed one more time. So, the optimal approach is to end the loop when the timer is greater than, or equal to 5. But there is no guarantee that the timer will be checked at 5 seconds exactly. So we cannot definitely avoid the up to 0.01 seconds additional running time. Well, this additional running time is insignificant, thus it is definitely not a problem. Let us now see our program in action. The 5 seconds are over. During these 5 seconds, 2 obstacles occurred and OD remained stopped until the obstacles vanished. We are now going to enhance our program and calculate the total time during which OD was stopped and the total time during which OD was moving. To do this, we must learn how to calculate the sum of many numbers. Let us assume that we want to find the sum of many numbers that we do not know in advance. All we know is that each of these numbers are stored one by one into the same variable, which we call number. Each time a new number is stored into this variable, we have to add it to the already existing sum, stored in a variable called sum, which we have initially set to 0. Here is how this works. A new number has arrived. It's 7. The initial sum is 0. We have already seen how this instruction works. The produced value is finally stored into sum, which now becomes 7. Again, a new number has arrived. It's 5. Since the value stored in sum is 7, the new produced value is 12, and it is stored in sum. Up to now, the numbers 7 and 5 have arrived and the value stored in sum is 12. The next number to arrive is 3. Again, the produced value is 15 and it is stored in sum. It has now become clear that the value stored in sum is the sum of all the numbers that have arrived so far. Thus, we now know how to sum many numbers. Let us now return to OD and review what happened, focused on the value of the obstacle sensor. The sensor returns either false, which means no obstacle, or true, which means obstacle. Here you see the value of the sensor as time passes. However, recall that we do not know the value of the sensor at all times. Instead, we check the sensor very frequently. If we were to put a mark on each exact time point during which the sensor was checked, we would see something like this. Let us now see how to calculate the time duration of an obstacle. An obstacle appears when the value of the sensor changes from false to true. This means that each time we check the sensor, we need to remember its previous value in order to decide if an obstacle has just appeared. If this is the case, we reset the timer and start measuring the duration of the obstacle. When the sensor returns false, after it returned true, we conclude that the obstacle has disappeared. The timer's value is now equal to the duration of the obstacle and we store it into a variable. To be consistent with the previously presented algorithm that produces the sum of many numbers, we name the variable in which the duration of the obstacle is stored, number. Now we can use the algorithm we already know to add this number to the sum of all numbers. In the end, the variable named sum will be equal to the total waiting time. Here you can see the program that calculates the total waiting time, but we have slightly changed the framework in order to reduce the length of the program. In particular, there are no motors, so OD is in fact always standing still. When an obstacle appears, we assume OD is waiting, otherwise we assume OD is moving. After the lesson, you can add the commands that manipulate the motors. We have also increased the total time to 10 seconds, so that we have enough time to put a few obstacles. Let us focus on this code. We have a few variables that we need to explain. we understand obstacle duration and total waiting time. They have replaced the variables, number and sum, that we saw in previous examples. In the beginning, we set the total waiting time to 0. Then, each time we have calculated a new obstacle duration, we add it to the sum, that is, to the total waiting time. However, these variables are not enough because we only have one timer that we reset in the beginning, in order to count the 10 seconds, which is the duration of the whole program. Thus, we cannot afford to reset the timer each time a new obstacle appears. Or we can, but we have decided not to. By the way, what is your opinion? Can we reset the timer each time a new obstacle appears and still be able to count the 10 seconds? Anyway, we have decided to reset the counter only once, in the beginning of the program. Following this choice, when an obstacle appears, we store the current value of the timer in the variable called obstacle start time. When an obstacle disappears, we store the current time in the variable called obstacle end time. Then we can simply find the obstacle duration by subtracting the obstacle start time from the obstacle end time. Finally, just before the loop is executed again and the sensor is checked, we store the value of the sensor in the variable called previous sensor value. This way, each time we check the sensor, we can determine whether an obstacle has appeared or disappeared because we have stored the previous value of the sensor. According to what we have already explained, a new obstacle appears when the sensor's value is true and the previous sensor's value was false. Similarly, a new obstacle disappears when the sensor's value is false and the previous sensor's value was true. A last detail remains. Let us assume that the loop is executed for the first time. Then, the variable named previous sensor value cannot have a value since the sensor has never been checked. Similarly, the value stored in the variable named total waiting time becomes equal to its previous value plus the value of the variable called obstacle duration. But during the first execution of the loop, what is the previous value of the variable named total waiting time? Well, by giving appropriate values to these two variables before the loop, we have addressed this issue. The total waiting time is set to 0 because it actually is 0 when the program starts. Also, we have set the previous sensor value to be false, thus we have assumed that initially there exists no obstacle. You can now build this program and execute it in order to see what happens. And now some more thinking. Is this program correct? Before saying yes, consider what happens if the last obstacle remains until the end of the 10 seconds. Are we able to add the duration of the last obstacle to the total waiting time in this case? You can execute it yourself and see what happens then. Can you find a solution so that our program works correctly in this special case? Are there other special cases that you have to consider? Special cases are often the cause of program failures. And although you are not expected to program like an experienced programmer yet, you need to keep this error in mind. Also, can you now check if the program that counts the obstacles, presented in the previous lesson, counts them correctly in case that the last obstacle remains until the end of the program? Here are some interesting questions. Answering them may help you reach a higher level of understanding and enforce your programming skills.